Hey everybody, here's our second Game Salad tutorial in which I'm going to go over the material that we covered in class last week so that you have a chance to really work through it again step by step and piece by piece. And also I'm going to introduce some new concepts that we didn't talk about in class or talked about only briefly in class. I'll go into a bit more detail in the tutorial, and you'll be responsible for that material in the quiz and in-class project. I'm going to be a bit more specific in the first part of the quiz project on Monday, asking you to do some very specific things using the tools and techniques that I cover in the tutorial, as well as there being a creative portion where you can take those same tools and techniques and really create on your own and hopefully produce some interesting and surprising uses for the same small set of techniques that we're going over. And as I mentioned also, if there's something in the tutorial that you don't feel you fully grasp, be sure to spend a little extra time on it, because I really want you to have the conceptual understanding of these tools so that you can use them not just in the way that I've shown them, but you can take the ideas and apply them in lots of different situations in your own work. So, moving into Game Salad, I'm going to create a pretty standard scenario where we have some walls and floors and a game functions actor who will handle procedures and behaviors that don't necessarily belong to a specific actor on the stage. So the game functions actor serves as kind of a director or a controlling function that allows us to have procedures that aren't attached to a specific actor. I created a simple image that I'll use to make a few more actors. And I'll call them red, green, and blue. Now notice at the moment they're all white, but if I go into each one, I could adjust the colors. Since white is the presence of all colors, and we talked about this briefly in class, white is the presence of maximal red, or red of 1, maximal green, and maximal blue. In the color theory of light, if you add red, green, and blue together, you get white. So in my red actor, if I remove all the green and all the blue, all that's left is the red, and the actor appears as red. So I can do this also in the attributes of my green my green actor, removing all the redness and all the blueness, and in my blue actor, removing all the red and all the green. And this is going to be an important concept, and we'll spend more time on this in class. But just to start getting the idea in your head that, first of all, colors in light, so colors on our screen, function differently than paint. We wouldn't ordinarily think of mixing red, green, and blue to get white, but that is in fact how the color theory of light works. All colors can be made from red, green, and blue, with black being no red, no green, no blue at all, and white being maximal red, maximal green, and maximal blue. And these numbers are expressed as values between 0 and 1 in Game Salad, where 1 means the most, a red of 1 is the most red, and a red of 0 is no red at all. And in between we have decimal point values. So if I want to make a dark blue, I can make a blue of 0.5, and you see my blue becomes quite dark. For right now, we'll stick with bright red, bright green, and bright blue. We call these primary colors: primary red, primary green, primary blue. I'm also going to color my game functions actor just so we can see the game functions actor on the stage. So coloring the game functions actor orange. And the game functions actor does have to be on the stage in order for its behaviors to function. So I'm going to make some walls and floors, put them off the screen. I'm using Option, click, and drag to duplicate. Sizing them so they're in the scene but they're out of the viewable area so we can't see them. And I'm going to put my game functions also in the scene but out of the viewable area. So the first thing we looked at was the timer behavior. Inside of game functions, I can create a timer, and timers can do things periodically, meaning every so often, or they can do things at a delay, meaning after a certain amount of time. So let's begin with doing something periodically, every so many seconds, let's say every 2 seconds. And then what I want to happen every 2 seconds goes here. For instance, spawning an actor. I'll spawn the red actor every 2 seconds. Let's go back and add a few details to our actors. First of all, our walls and floors should be immovable. So I'm going to go into the physics section and remove or set the movable attribute to 0, meaning this is not movable. Things that only have 2 choices in computing are called booleans. A boolean means yes or no, on or off, 1 or 0. So I'm setting movable to 0, meaning the movable attribute of this actor is false. It is not movable. If I click it, that sets the movable boolean to 1, which means movability is true. Yes, it can move. If I turn it off, no, it cannot move. Similarly, in the walls and floors, I'll give them collide attribute so that red, green, and blue all bounce when colliding with the walls and floors. Red, green, and blue. And to duplicate those, I used Command C and Command V, copy and paste. In my game functions, as we saw, every 2 seconds we're going to spawn a red actor. Now here we face a problem. Look at where our game functions is. It's on top of the walls and floors. And the walls and floors have a collide behavior for the red actor. So if I create it here at the same location as my game functions, it's going to bounce unpredictably, probably off into space. It's never going to actually come onto the stage. So we've looked at this idea before, but let's look at it one more time. Here I have a position where this spawning can happen relative to the game functions actor. And so I want to spawn this red actor below the game functions actor. So I want to spawn it at a position, a vertical position that's below where game functions is. Let's say 100 pixels below. So I would spawn at a position of negative 100 pixels vertically, 100 pixels lower than where the actor is. So if I preview this, my red actor comes into being 100 pixels below where my game functions is. And if I said 200 pixels below, it's going to appear even lower on the screen. So spawning, every 2 seconds, spawn the red actor 200 pixels below the position of game functions. And we see it appears lower on the screen. 300 pixels would make it appear even lower. I'm going to leave it at 100. Let's give our red, green, and blue actors some gravity, some acceleration, downward acceleration. I'll copy this and paste it into my green actor and paste it into my blue actor so that all the actors are affected by downward acceleration, which is gravity. One other thing I should point out is this acceleration should be relative to the scene. Acceleration that's relative to the actor we'd call thrust. It's the acceleration relative to the rotation of the actor. But if we want to be gravity, we want it to be relative to the scene. You can think of the scene as the Earth. Relative to the Earth, there's a constant downward pull. So I'll make sure to set this relative to scene in red, green, and blue. And now, every 2 seconds, the red actor that's spawned is going to fall. And notice the nice visual collage or animation I get by not having a collision behavior here. Red just passes through itself. Red only bounces off the walls and the floors. It does not bounce off of other instances of itself. So let's go back in to these and say that red has a collide behavior where it bounces on actors of type red, green, and blue. So now red will bounce off of itself, and greens and blues. I can take all three of these by shift-clicking them to select multiple. So I click the first one, and then I shift-click the second one and shift-click the third one. I'll copy all three of these and place them into my green actor and place them into my blue actor. So now we see a much different scenario because reds bounce off of each other. And because the physics engine has a little bit of built-in instability, a little bit of built-in randomness, that bouncing breaks up the column of falling actors and allows them to bounce around the screen. Now, one of the things with a periodic function like this is that I'm going to keep getting red actors every 2 seconds forever, and these actors live forever. And so some of you discovered this on your own, but here's another use of the timer, which is you can give these actors a lifespan. Instead of every 5 seconds, I can say after, let's say after 20 seconds, this actor will destroy itself. So these actors appear every 2 seconds, and after they're spawned, they live for 20 seconds and then destroy themselves. This keeps the screen from filling up too quickly. And that's the second use of the timer. Rather than periodic, every 20 seconds, it's a delay. 20 seconds after it's born, this thing happens. Also, we can use this same timer, the same delay, in the game functions to spawn one of our other colors. So we'll say every 2 seconds spawn a red, and after 5 seconds spawn a green. So now all of these rules, all of these timers are going to interact with each other. Every 2 seconds we get a red, after 5 seconds we get a green, and after 20 seconds of being spawned, red actors disappear. So here's our first red, 2 seconds later, next red, and there's the green, 5 seconds after the beginning. Another use of timer would be to spawn inside the actor. So for instance, we could put a timer here that says after 5 seconds, the actor, not the game functions, the actor is going to spawn a blue actor to the right of itself, 100 pixels to the right of itself. And here's using that position again, relative to actor. So relative to the current position of this red actor, 5 seconds after it's born, it gives birth to a blue actor 100 pixels to its right. So here comes our first red, and after it's been alive for 5 seconds, it produces a blue. "100 pixels to its right, relative to actor." And the blues live forever as well. It's only the reds that will disappear after 20 seconds. So we can see the reds start to die out after they've been on the screen for 20 seconds. This is going to result in a high blue population, a decreasing but then constantly updated red population, and still only a single green on the screen. So one thing we can do, see how our behaviors area here starts to fill up with things. We can collapse these. They still work. We're just not showing the details. We can also, by shift-clicking, select a group and create a group of them and call this collisions and collapse that. And now much less space is being taken up. We'll call this lifespan. I'll call this spawn blue. And now we have plenty of space to work. So we can also add rules based on collisions. For instance, when a red collides with another red, something about it changes. This is an if-then statement. If a red collides with a red, then, and now we can use that change attribute behavior that we looked at in class. We can change something about it. So remember that attributes are the qualities of a thing, the thing that describe the attributes describe an object in the game. And also there are attributes of the game itself and of the device the game is playing on, such as the computer or an iPad or an iPhone. Right now we're just looking at the actor's attributes. And we'll say when a red collides with another red, it shrinks to 25 pixels in width, and option click and drag, it also shrinks to 25 pixels in height. So basically shrinks down to 25 by 25. And in this if-then statement, we can have as many things as we want in the then portion. And all of the behaviors that go in the then portion will happen when this condition is met. So we can call this if red collides with red, then shrink to 25 by 25. So now whenever reds touch each other, they become small. But the interesting thing about this, and the thing that limits it a little bit, is we can't say, using this form of the rule, make the red actor smaller each time it collides. All we can say is, when it collides, change the size to this fixed value. So once they're already 25 by 25 pixels, if they collide again, the rule is still triggered. But the rule is change the size to 25 by 25. They're already at 25 by 25, so they can't, the rule doesn't allow them to get any smaller. So let's, with the blue actors, try a different approach. In the blue actors, we'll use the same form of the rule and say when a blue collides with another blue, it gets bigger, and each time it collides, it gets even bigger. That's the same change attribute. We're changing the blue's width, but we're not changing it to a fixed value. We're changing it to a value relative to its current value. So if it's currently 100 pixels, we can enlarge it by 10 pixels. And here we click on the E, and this brings us into a slightly different editor, the expression editor. And from the the down arrow pull down, we choose the same attribute. So we're saying we're changing the attribute width, and we're changing it to the previous value of the attribute width plus a certain value, let's say plus 10 pixels. So the width will grow by 10 pixels each time there's a collision between two blues. So to sort of rephrase this, we're saying if a blue collides with another blue, then measure its width, add 10 pixels to that width, and set its new width to the resulting value. So if it was at 50 pixels, now it'll be at 60. But if a collision happens at 60, we add 10 to that and it becomes 70. So our reds rule still shrinks them to 25 pixels right away, and then there's no further activity. But when two blues touch, they get a little bit bigger with each collision. And we set it so the collision only affects their width. We could certainly copy this and paste it and have it also affect their height so that they grow proportionally. And you can't type in, I mean, it would be nice if you could type self.size.height here, but you can't. You have to use the down arrow and select the attribute you want to change. And then you type in the mathematical part of it yourself. So self.size.height plus 10. Increase the height by 10. And now we should see them grow proportionally. And indeed they do. With every collision, the blues get bigger. Now remember, the reds have a lifespan. So after 20 seconds, they destroy themselves. The blues do not have a lifespan. They're just going to keep colliding and keep growing indefinitely. So we can say, for instance, and this is a new type of rule. I'm going to group these collides. And this rule is if collide with blue, then grow 10 pixels in size. We'll add another rule, and this rule is going to be about an attribute. Which attribute? Let's make it about the width. And here we have a comparison. So this rule is based on what's happening with the width. So we can say, for instance, if the width becomes greater than 200 pixels, then something happens. For instance, we destroy it. So this rule is if width is greater than 200, so if it's grown, it starts at 100 pixels, and so after it's grown enough time that its width is greater than 200, then destroy. So essentially, they're going to grow until they pop. So the reds age until they die. The blues grow until they pop. Let's watch this one. There. So let's look at one more possible application of this type of rule and comparison. Let's take, we haven't done much with our green, so let's look at our green. And again, I'm going to shift click to select all three of these collides and create a group to clean up my screen a little bit. And I'm going to create a rule about collisions and say when this actor collides with a red, or this actor collides with a blue, then something happens. Now, at the moment, that's actually not what this rule says. This rule says when all conditions are valid, meaning when both of these things happen. But I want it to be when any of these things happen. So this makes it an or statement. When any of the things listed below happen. So if it collides with a red, this happens. Or if it collides with a blue, it also happens. And here we will change the color attribute. Right now the only color it has is green. So we'll take its green and reduce its green. Let's reduce its green by 20%. So we'll say green's green minus 0.2. So remember that 0 is black and 1 is maximum green. So if I reduce it by 0.2, that's taking away 20% of its greenness. So if its green was 1, then after a collision its green will become 0.8, and then 0.6, 0.4, 0.2, and then 0. It'll be black. So let's see that happen. With each collision, the green gets a little darker until it's gone. It collides a lot. I'm going to have it appear at a different location so it collides a little less often. After 5 seconds, game function is going to spawn the green actor not only 100 pixels below it, but 200 pixels to the right of it. So now when green is spawned, green's going to appear to the right of game functions. And so now it's going to live a little bit longer because it's going to be a longer time before it ends up colliding and darkening and darkening and darkening. Now it's still there. It hasn't actually been deleted. It's just a black shape that's still on the screen. We haven't destroyed it. And to illustrate that, why don't we give it back a little bit of some other color so that we can see its shadow still on the screen. We're gonna put a little bit of the red back into this green. So once all its green is gone, after a series of collisions, it'll have a little bit of red left in it. It'll be a dark red. See it? That was our green one. So if we actually want the green to be destroyed after it runs out of greenness, we need another attribute rule. Get darker, darker, darker. Now I've made it a very dark red, but it's still on the screen. So let's make another attribute rule. We create a rule. This rule is about an attribute. And the attribute we're looking at is green's greenness. And we can say when its greenness equals 0, meaning when it's been darkened by this rule until there's no green left, then something happens, such as we can destroy it. And our green gets a little darker with each collision, darker, and then when the green is reduced to 0, it is actually removed from the stage. There's no more red shadow floating around. So I think that pretty much covers everything that we talked about in class. And you hopefully can see how these simple rules can be combined in really an infinite number of variations and combinations to produce different kinds of visual compositions, kind of behavior on the stage. So I want you to be able to replicate the behaviors and the rules that I'm showing here, but also to be able to take these same ideas and create something different with it, something that interests you, and something that is in contrast, so that you can make things that contrast with each other, so that not everything you make ends up looking the same. If you have any questions after you've gone through the tutorial, please email me, and I will expect you on Monday to not only be able to do some very specific tasks that I request based on this tutorial, but also to apply these creatively in your own visual compositions. And of course, feel free to use sound as well. Sound makes for a really interesting component, as you saw in some of the demonstrations in class last week. Thanks. I hope you're having a great week.